My name is Dr. Danny Elvidge and I'm Senior Lecturer at Building Physics and Services at UWE in Bristol, and this is a short video talking about mathematical units, specifically SI units. So the two gentlemen here, Gabriel Malden and Louis XVI, I apologise if I am not pronouncing their names correctly, were responsible for starting the modern system of scientific units, the SI units, System International. Until the SI units, these standard units, were begun, you had many different units used in different parts of the world, in fact even within one country. So I asked a group of students to start naming different types of units in a lecture recently just for length, and they came with all of these different units, all of them used in the past 100 or so years to measure length. So we've got things like the imperial system with yards and miles and inches, etc. And we've got the more modern millimetres, centimetres. We've also got a few more obscure units. For instance, hands for measuring the size of horses. You have furlongs, which is still used in horse racing. We've even got units like parsecs, which were used in science fiction as a measure of time, but are actually a measure of distance. So this is a very confusing system. If you don't have one unit, you won't know what measurements are being used. In Louis XVI's time, if you were to buy a dozen eggs in one part of France, you would not get the same number of eggs as buying a dozen eggs in another part. A yard of cloth in Lille, for instance, would not be the same as a yard of cloth in Paris. And this became very complex. So it was decided to make a single unit that everyone would work from. Those are the modern SI units. And these problems were still occurring up until around 1999, the year 2000. This is an example of when units do get mixed up and why using SI standard units is so important. So in 1999, NASA lost a $125 million Mars orbiter because half of the team were working in imperial units and the other half of the team were working in metric. So let's have a little look at what make up the standard units we use in science today. We'll start off with the 7 SI base units. So when I say base unit, I mean the units on which all other measurements are based. You can take a moment and try and figure out how many of those you might get. So here are the 7 standard base units. For distance, mass, time, temperature, electrical current, quantity, and luminous intensity. And each one of these quantities is given a unit, and those units are, for distance, meters, mass is kilograms, time is measured in seconds, temperature is given in Kelvin, electrical current is given in amperes, quantity is given in moles, and luminous intensity is given in candela. Now, many people won't encounter things like amperes, moles and candela, but I'm imagining that most of you are familiar with meters, kilograms and seconds. So each one of these units is given a shortened symbol that we can use in calculations. You'll be familiar with the first few. So meter, small m, mass, kilogram, time, small s for seconds, temperature, K for Kelvin, electrical current, A for ampere, moles is given MOL, and a candela is CD. So whenever you see these symbols used in a textbook, you'll know that they relate back to these quantities. So one of the interesting things you might want to note is that some of these are lowercase letters and some of them are in capitals. So if you look here, that Kelvin and ampere are given in capitals. This is because they're named after people. There was no Mr. Meter, so it's a small m. There was no Mr. Kilogram. However, there was a gentleman named Kelvin and a gentleman named Ampere, so those are given capitals. So let's look at how these might be used. What if you need to measure the speed of something? What units would you use? So this is when we start looking at derived units. There was nothing in those 7s that can determine speed alone, just distance and time. So speed is distance divided by time. How far do we move in a set period of time? So if we know that the standard unit for distance, here's the base units, is meters, and the standard unit for time is seconds, we know that any measurement of speed must be given in meters per second. Often you'll see this written as m/s with a dividing line between, and you'll sometimes see it as ms-1. Now, I've no need to understand exactly why that is at the moment. All I want you to know is that the standard unit for distance is meters, the standard unit for time is seconds, therefore when we measure speed, it must be meters per second. The useful thing about this is if you're doing a calculation, you should now be able to look at the numbers you're giving and think, does that seem reasonable? When you know what the unit should be, you can start working out if your answers are right or wrong. So meters per second is a derived unit. It's been derived from the base units of distance, meters, and the base unit of time, seconds. Let's have a little look at something a bit more complicated now. Take a moment, relax, think of something happy. If you don't get it first time, do not worry. I just want to explain some of the more detailed derived units. Let's look at some more complicated derived units. So units which have been derived from those 7 base units I showed you earlier. So let's have a little look at some. I'm going to talk about their quantity that we're talking about, the name given to it, the symbol used in science and mathematics, and the base units from which they're derived. Taking one at a time. We have force, energy or work, frequency, so this would be in signals, in sound for instance, pressure, and power. Now there are many other ones, but these are the ones I'm going to use in this example. So the name given to the quantity force is a Newton. The name for the unit which we used in energy is a joule. Frequency is hertz. Pressure is Pascal. And power is a watt. Now in textbooks and tables you'll see these abbreviated to just give you a symbol. Newtons, N. Joules is a J. Hertz is HZ. Pascals is PA. And a watt is given as a W. One of the things that's worth noting here is all of these symbols have been given capital letters. And just like we talked about earlier, these are in capital letters because they're named after famous scientists. Newton is named after Isaac Newton. Hertz is named after Heinrich Hertz. Pascal after Blaise Pascal. So each of these, when you write them out, should be given a capital letter. So these are derived units. So a Newton, when you refer to it, is actually made up of a kilogram per meter second minus 2. Don't worry if you don't understand exactly what that means. I only need you to understand that a derived unit is made out of base units. A joule is a kilogram per meter squared per second. Hertz is 1 over a second, so how many times something happens per second. Pascals are kilograms meters per second. And the watt is a kilogram meter squared per second. I once again say that you do not need to understand how these base units are used at this stage. I just want you to understand that a derived unit, like a Newton, has been derived from, made out of, a series of those first 7 base units we talked about earlier.